Hello, thank you for coming to SIG School Scholars. Today, we'll be looking at uniform circular motion. And really what that is motion of an object about the center of a circle C of radius r. And what we're saying is that the tangential velocity of the object, tangential to the path it's taking, does not change. The magnitude of that velocity does not change. So, at any time, this object traveling in a circle of radius r and center C will have the same velocity at every point on the path. It's not accelerating in that way. It's however, there will be an acceleration, because recall that the definition of acceleration is that it is a change in the magnitude or the direction of a velocity. So the rate of velocity does not have to change for there to be acceleration. In this case, the speed of the object is not changing, or the velocity is, because it's changing direction. So, and it must change direction if it is going to follow a curved path. So, we're going to say again that this is a circle, radius r, center C. We're going to say that we're looking at a small time interval. Which is delta t. Okay, and during that time interval, the particle moves a distance delta L equal to v delta t. And that delta L is an arc along the curve of the circle. So, now what we need to do is find a formula for that velocity. A formula for that acceleration towards the center. So, we can write that v1, v2 are two sides of a right triangle, and the third side is their vector difference, delta v, and it is directed along the radius or towards the center of the circle. So this angle here is a small angle, delta theta, and it's small because it is the angle that subtends the arc delta L. We already said delta L will be small because delta t is small, which means the theta must also be small. So let's use blue. Okay, so so this is for small times. For small times, this delta L here is going to equal the linear distance between the object's position at x1 and x2, or at time t1 and time t1 plus delta t. So, for very small times, that arc is going to equal a straight segment between those 2 points, those 2 positions. So then we have another right triangle. That's the case. And this right triangle and that right triangle are going to be congruent. Or they are going to actually be similar. And we demonstrate that by writing that these 2 ratios are going to be equivalent, but only equivalent for small delta t, for small time. As the time approaches 0, then this will go to a equality. So what we need to do is solve for delta v. And we're going to use this formula to find a formula for our inward acceleration. So when we divide both sides by delta t, we get a, and we label this AR, or radial acceleration. So we call it radial acceleration because its direction is along the radius of the circle. So we have and we know delta over t will be v. So what we have is our formula for radial acceleration, which is also called centripetal acceleration. And that is centripetal acceleration equals v squared over r. So, in summary, what we have here is that if we have a circle, if we have an object traveling through space in a straight line with velocity v, an object traveling in a straight line with velocity v through space. And remember that if there are no net forces acting on an object, then it will travel in a straight line forever. So that's basically what we're saying here. But then what happens is that a inward acceleration, or a force must be applied to this object to cause it to follow a curved path, and that force must be applied at all times to keep the object following this curved path. So basically we have something that looks like this. An object is made to follow this curved path with a tangential velocity because of some radial force directed along the radius towards the center of the curved path. And the acceleration caused by this radial force, centripetal acceleration, is going to be perpendicular. The acceleration, that delta v, is going to be along the radius as well. Acceleration is going to be along the radius. The acceleration and the force are going to be in the same direction, because a force causes an acceleration in the direction which the force is applied. So the acceleration is also along the radius, and the acceleration is the change in velocity that occurs because the object is continually changing direction over the time period that that change in velocity occurs. So, an object moving in a circle of radius r, at constant speed v, has an acceleration whose direction is toward the center of the circle and whose magnitude is v squared over r. And what this formula means is that the greater the velocity of the object, the greater the acceleration that must be applied to it to cause it to follow the curved path. Because the change in velocity that causes it to curve around the circle must occur quicker because the object is moving. Okay, it covers a larger L and a shorter t, and a short t, because it's moving faster. If we were to increase the radius, however, the acceleration would decrease because the L would decrease. I mean, the L would increase because the circumference of a circle of larger radius larger radius in another circle is going to be larger. So in a given time, it will cross, well, cover less L, I guess you could say, less of an arc. So, based upon that, we can redefine velocity. Can give another definition for velocity that will be very useful for our efforts. That is 2 pi r over t. 2 pi r, as you should recall from geometry, is the circumference of a circle. T is going to be period, or the time it takes for one complete revolution around the circle. So 2 pi r is going to give us some distance or length, and t is going to give us time. So it's still going to be meters per second, a distance over a time. This is telling us how large one revolution is, and this is telling us how long it takes for it to complete that one revolution. And then frequency is defined as the reciprocal of period. Frequency will equal 1 over t, so we can also write as 2 pi r f. Okay. Thank you for watching the video. Want to make a video on a specific topic, just leave a comment either in the comment section below or on our website at sigschooltours.wordpress.com, and we will try to fulfill your request as soon as possible. Thanks.